necessarily get killed? Can it get reduced or affected if there is another source of turbulence in the disk itself, like convection or what is crowd turbulence or whatever? So how to approach this? We are doing this sharing sheet MHD calculations, trying to figure out what is going on in a system where there is both MRI and then forced turbulence. Actually, the motivation to this doesn't come from accretion disk, it comes from galaxies, but nevertheless, and also from these results. So actually, the non-ideal MRI theory, linear theory, predicts that actually if there is ohmic dissipation eta for some source, then the dispersion relation will look like this, which practically means I will not go into details of the solution and stuff like this. This is basically the same dispersion relation you normally see in the MRI stability analysis. This is a new term, and this is a new term, and here is the effect of ohmic dissipation. But what does the solution to this mean in practice is that if the dissipation rate approaches and exceeds the growth rate of the MRI itself, then you can suppress MRI because it doesn't grow at all. And for the fastest growing MRI mode, this comes from the ideal MRI analysis. So the maximal growth rate of MRI can be expressed in very, very simple terms with the shear parameter Q and omega. And if you just use this information from all this mess, then you can just express this criterion in a function of Q and omega, and then of course you have to assume some length scale which is diffused. So K now represents here the scale of turbulence or scale of whatever process is going on in the disk system. And this is just a result from 1D numerical simulation to confirm what I just put down as a form of equation. So this is a diffusion time scaled by the maximal growth rate for two sets of calculations with varying shear parameters. So this is the Keplerian shear disk, and this is kind of like a galaxy where the rotation curve is flat. And then you just measure the growth rate of MRI, and this is just a trick to match these two curves exactly at the point where the growth rate of MRI matches the dissipation time scale. So when you approach the limit, then you get a very strong reduction of the MRI growth rate, which approaches 0. So at least in in 1D this works quite well.
What is this tau d thing?
It's a dissipation time scale.
So it's eta times k
Which is
squared?
Yes.
given
And
pi watt by
Sorry?
the which is given pi watt by the resistivity. Huh?
Well, resistivity,
Yeah.
or then if you have turbulence, you have enhanced diffusion, then you have like turbulent ohmic diffusion, which goes in there.
So you're
So this is-
basically by turbulent diffusion then, yeah?
Yeah.
Right.
Basically, the idea is to replace this by turbulent diffusion.
Mm.
And then, of course, the whole game is how you can estimate this from your whatever turbulence there is. If you are lucky, or if you're dealing with something which is isotropic, as I am in this talk, then of course you can replace this with a very simple formula. And then you can make further assumptions when the MRI can be suppressed. Okay, and the application, what it has motivated me is really galactic disks, which really contain a lot of sources of turbulence. Of course, the MRI is also possible because Q equals 1 in galactic disks, so it's possible that MRI is there as well, but we also know that there are supernova explosions which kind of outpower any other source that there might be. So this is just a perfect example of this, where this analysis might apply. And actually I have done this, and the result of this, combining the linear results with some observational data like supernova frequencies as function of radius. And then you have to estimate turbulent diffusion, what comes from the numerical models. Then you can show that actually supernova explosions suppress MRI in most of the, or let's say considerable amount of the visible disk, I mean in radius. And only in the outer parts of galaxies the MRI could survive, basically, unless there is gravitational instability, thermal instability strong enough to suppress it again. Okay, in accretion disks there may be some sources of turbulence which may also be important in this aspect. So of course, in the context of accretion disks, the question maybe is, the relevant question is maybe that how does the angular momentum get affected by this turbulence rather than does MRI get killed or whatever. And then of course it's interesting to know how this linear prediction works. So does it really, in these MHD simulations, can you really use this very, very simple linear prediction to know when MRI is actually getting suppressed? And of course then the ultimate question is, what I did for galaxies, it seems that most of the galaxies where supernovae are frequent, they are in the regime of MRI suppression. But in accretion disks, I don't know about that. So how we do investigate that, this issue then? So the initial idea was just to take a flow that is known to become MRI active. And now I refer to first to Toby and then also to Petri. The model is very much the same. It's actually almost the same as yours, Toby's, I mean, if you recall. So we have also taken the isothermal assumption, and then we just take, instead of having an elongated box in the azimuthal direction, we take actually a cube of 2 pi, then just have a magnetic field, weak magnetic field initially, and then there is this shear. And then the additional thing on top of this, what we do is that we stir the gas with a suitable forcing function at a certain wave number, so we can specify the wave number at which we force, which of course helps us to understand what is going on in the system. And then we just, what can we do? So how do you know that MRI is really active? So you usually monitor the stresses, and then you vary the amplitude of forcing, which I call F here, and then you just try to see what happens to the stresses, stress ratios, whatever, as function of F. At the same time, we can now, because this is isotropic case, forced turbulence, we know a result from other investigations that we can, in this particular case, express the turbulent ohmic dissipation with this very simple formula. So it's 1/3kF times URMS. So we can actually write or simplify this limit further, so we can write it down as the URMS, and it turns out to be something extremely simple, depending again of Q omega and Kf. So we know that according to the linear theory, above this limit, we are supposed to see something. So then we have done actually, well, the first thing what you have to do is to get a reference from a pure MRI simulation, and we just chose the Keplerian value. And, well, it looks, everybody more or less knows how it looks. It looks like this. Toby has shown maybe a nicer thing. The time resolution here is not extremely good, but this is just the density, logarithmic density as function of time, so you see the effect of shearing. In this particular case, you don't see the waves, what Toby has shown, but this may be just lack of time resolution or whatever. So very characteristic of this system is that the Maxwell stress is always negative and larger than the Reynolds stress, which is always positive. And this stress ratio, quite generically, seems to be about 4. Then you get in this system we don't have any stratification, so we don't see any large-scale dynamo, in contrast to some earlier investigations of Axel and Barbus Holly and collaborators, where they really do get a large-scale dynamo. But here, as we don't have stratification, we actually only see small-scale dynamo. But nevertheless, we get super equipartition fields where the ratio of this should be magnetic to kinetic is 2 over that.
Hi.
Sorry.
What's your plasma beta?
Initially, it's something few hundred thousand.
Okay. And then
We have tried several plasma betas.
But that comes out of the simulation inevitably, right?
What?
Depending.
What?
The plasma beta?
Oh, you mean in the final
Yeah.
state,
Yes.
plasma beta? I haven't even calculated.
Okay. That's the same as saying what alpha is, isn't it? Essentially?
Yeah.
Which is 0.01 and less.
Yeah, then the first choice of forcing we used was for some reason, maybe because of the galaxies, because they do have helical forcing. So we just implemented helical forcing at the wave number 3, and for this we can now control immediately what is the limiting URMS where we should see something, reduction or whatever. So this is for all the calculations 0.15, which of course is determined by this choice of these and then omega and q. Since we don't vary q, omega or kf, then this limiting URMS is always this 0.15. So, well,
You are forcing the velocity here
yes,
and not doing anything to the magnetic.
no. So anyway, this setup is quite bad, because what happens there is that we get a large-scale oscillatory dynamo, which kind of contaminates the stresses. But nevertheless, let's see what it looks like. So first of all, the dynamo solution. This is the magnetic field, By. So you get very strong large-scale field, which is going like upwards in the box. Fine. So there is this large-scale dynamo, which is not the best case you can try.
And it's not oscillatory, it just builds and then...
Yeah, it goes, there is a wave, which is goes like up and starts from, like in the vertical direction. Anyway, when
Although
you
you
look
do
at
say it's oscillatory.
So it is so then it is oscillatory.
Well, but it's oscillatory in the sense that there's a...
Yeah, but that's because just periodic, you have periodic
Yeah,
boundary
it's
conditions.
yeah.
just going around and around.
yeah,
and around,
Yes.
that's because of that. Yeah, so if you just then try to look at the stresses, even though you know that there is this dynamo, so what do you basically see is that the stresses, they just grow with F. And I have now normalized them to the pure MRI case, which is right there, so that's why they start from 1. So the forcing goes from very small to very high. The limiting URMS is here, so you would expect suppression regime here and no suppression here. So, well, the stresses start growing immediately, and they more or less monotonically grow. The Maxwell stress grows a little bit more faster than the Reynolds stress, so you can just imagine what happens to the ratio or total stress. They are both growing. So this is now the stress ratio. So the Maxwell stress xy and Reynolds stress xy. So it's just not affected at all with the forcings that URMS is less than this limiting URMS, but then they start growing quite rapidly when the forcing is more or producing more turbulence than this limit. Fine, so that wasn't the best setup, so how can we change that? The easiest choice, of course, is just to get rid of the helicity, because you know that this causes the dynamo action. So we just now use non-helical forcing with exactly the same parameters. But then, again, there is a dynamo. But this is not the alpha squared dynamo, alpha omega dynamo, or anything. It's more or less what is called as the fluctuation alpha shear dynamo. And this generates fields which is look like this. There's no use of showing a video because in the video you don't see this. So this is very sensitive to the forcing function actually. So when the forcing is weak, this is in the limit where MRI also is supposed to work. This is in the limit where there is supposed to be no MRI. Anyway, there is a large scale field, but it's like, I don't know, it comes and goes here and there. There is no clear periodicity on anything.
So that's already averaged over the toroidal direction, right?
So this is now time, and this is, this is, yeah, yes,
Yeah.
No, it's what, sorry?
It's averaged already
Averaged.
horizontally.
horizontal average.
This is higher.
So this is height.
This is
Yes.
Yeah, anyway, so when the forcing is weak, so you get this, but in here there should not anymore be any MRI. So the thing looks like that. Anyway, we again measure the stresses and look what do they do. So now the Maxwell stress, which was very strongly growing in the helical case, doesn't get affected much on the left and then saturates very quickly. But the Reynolds stress doesn't like to stop at all, so it's just growing. And because of this, of course, the stress ratio doesn't do much here, but then it decreases very strongly when you are on the right from this limit.
So,
And it looks like this.
no,
Oh, sorry.
Maybe no, finish your talk, sorry.
Yeah, so this is how the stress ratio actually looks like. So no effect here and very strong effect there. So obviously, even that is not enough. So basically what we need now is some sort of control runs where there is absolutely no MRI, so that we can kind of subtract these two effects from each other, whatever there is, what sort of dynamo there is, or MRI. So then we just came up with the idea that fine, there is certainly no MRI if the Q parameter is negative. So we then changed the sign of S and omega. So then if they are both negative, then we get a negative Q. So then we just make this trick, and then we can be sure that there is no MRI. And then we can measure the whatever, turbulent velocity, turbulent magnetic field, stresses, whatever, and compare directly to the, just exactly the same calculation but with a positive Q. And then see if we can make any sense of the stresses. Because the stress ratios, they behaved in a way that this limit made some sense to the stress ratio, but not to the stress. So this is just the same non-helical set. Now every point matches with another simulation run, but with a negative Q. And from there we take the URMS squared to normalize the stresses. So when we do this, then the stresses themselves, both of them, get reduced. They get reduced even here, but especially the Maxwell stress, very, very strongly after the limit. So interpreting it this way, even the stresses and the total stress and so on, they get reduced in this regime, as was expected from the linear analysis. But just because I wanted to make this talk quite short, so what did we learn from this very, very simple exercise actually, is that even very, very weak turbulence, not very much higher the level of turbulence than the MRI itself, it really affects the MRI, not by killing it, but just affecting it. If the turbulence, additional turbulence, is helical, then you can expect a stress ratio which is growing, and of course total stress, which is totally unnormalized to anything else, it's also increasing. But if non-helical, then, okay, there are these dynamos to consider, but anyway, if there is non-helical turbulence, not even very high magnitude, then the stress ratio is strongly decreased, although the absolute stresses increase. And these changes seem to, at least the stress ratio, change only after this URMS limiting URMS is achieved. And then these negative Q reference runs maybe help to understand the system better, so that even by comparing these two cases, then you can see that the stresses actually decrease only after this limit. So this is to say that, okay, maybe if there is really some source of turbulence which doesn't necessarily contribute to the angular momentum transport in the same way as MRI, but it may still affect the MRI itself and the angular momentum transport from MRI. So that's more or less what I have to say. Thank you.
Questions?
So in terms of a simple formula, if we compare the RMS velocity to the Alfvén speed,
Well, the Alfvén speed doesn't come into the formula at all.
But you have
That's because of the gamma max doesn't depend on magnetic field. Gamma max depends only on Q and omega. Do you want to see that? Where was
the
it?
gamma from the MRI.
This one.
Yes.
Yes.
Is that the one you're talking about?
Yeah, or which gamma?
Yeah, the gamma from the MRI,
Yeah.
the growth rate from the MRI. I see.
Yeah, so
I see. So
then
you always, but that means you are having available a K on which can be very small, of course.
Yeah, of course. This now.
Or large, rather.
Yeah.
For the
Okay.
Korpi field,
Yeah. Well. Yeah.
which may then
Of
be.
course, in this special case, the definition of or determining what is K is very simple. But in some other contexts, it's not that simple, and then it can be very large or very small.
So, but it seems to me that the way you may want to do this, let's say if you have accretion disks that are MRI unstable, then you get an alpha structure like this, and you find that given the opacities, you have convection. Then it seems to me the way you want to, the natural way we think of this is to ask, well, first there's again the chicken and egg, but the convection has to be initially due to the MRI dissipation, okay? But then you actually have extra, let's say you have extra turbulence from the convection. The quantities I would compare is maybe a growth rate for the MRI to a growth rate for the convective mode, right? Which is not exactly the way,
Well,
because what you're doing here, you're putting it by hand. But if you imagine that you have a faster growth rate for an instability, it's not clear you're going to be able to drive the secondary one, I guess, is what I'm saying.
Yeah, okay, but yeah.
So
That's
so
of
you might
course then
determine
the process which is kind of faster will win the competition in the simulation. So how can you then know?
Yeah, no, you don't. Well, I guess.
I mean.
Yeah, but I guess I might determine the U.
I mean, here when you force the system, then the growth rate is always much faster than the growth rate of MRI. Yeah, so whatever is growing pretty fast compared to this.
But
Few orbits or
but he
whatever.
is basically asking whether this is still the right way to think about the relative importance of one over the other. If the growth rates become comparable, then there's a takeover.
Even here, the whole analysis is based on growth rates and diffusion rate.
And it does it, and now in
But
hindsight.
maybe I would say that if the convection growth rate is slower than the MRI growth rate, you might still get convection, but you might get a weak form of convection.
Yeah,
so
although
that
the
would be
growth
your.
rate of convection doesn't necessarily tell anything about the amount of ohmic dissipation, because it's ohmic dissipation which is going to act on your magnetic field, basically.
Okay, but
Yeah. Well.
I just.